Okay, so good morning. Uh, I will start my presentation regarding the redefining trust and reproducibility in open science through decentralization. This is a work in progress that we started at my master's with the supervisory of Dr. Rafael and Dr. Tiago. And now we are evolving this for the covering of another topics in the subject of open science. And my agenda will be first, we will talk about a bit about reproducibility and why the current model of open science is failing in terms of trust. Then I will characterize a bit about the centralized bottleneck, where I will present some systemic gaps in research data management, and then I will move through the solution, discussing a bit about decentralizing provenance, the path to trustworthy research, and then we draw some conclusions and open to the Q&A. It's very important first to get a canonical meaning of the word reproducibility, because this is very important to the whole discussion I'm presenting here. So reproducibility in the dictionary definition is the ability to reproduce or copy. And this ability of reproducibility underpins all the science endeavor, all the science research model that we currently practice today. And this is a very discussed topic in science in many domains. So aquí just to contextualize two very important papers. The first is a manifesto for reproducible science from Munafo and his team. And the other is a paper from Nature that questions if there is a reproducibility crisis. So, in fact, there is a crisis in reproducibility in science, and this crisis is well documented today and have very profound impacts in the research science. So this paper here from Friedman just presents here that there is a high rate of failure in reproducible science. So this is a compilation of several research that analyzed several papers in this N number here, stating that the rate of failure on reproduce research. So it's a very high rate, like 50% of the papers that a researcher tried to reproduce, he will not succeed. It's a very high rate. And there are four main dimensions of that are causing this problem. The first dimensions are related to, in this case, to preclinical analysis. And there is a specific dimension that is of our interest in our research, that is the dimension of data analysis and reporting. So our focus of our research is on this subject. But it's also important to note that there is financial impacts also on public spend on research that's not reproducible. So there is a lot of billions of dollars that are wasted on research that is not reproducible. So that's a very important matter on the science domains. And for our attention, we must first define what we are studying. So our question here is related to the research artifacts. So all the science is backed by the research itself, but also the artifacts that produce the evidence needed. So artifacts are any kind of digital media, in this case, that supports the evidence of our research. For instance, raw data, code, protocols, image, sounds. So any kind of information that is digitally stored is used as an empiric trail, as an evidence of research. So that's very important because this evidence will be used to prove the claims that a published article is stating. So it's very important for transparency of research, and all the evidences, they show the statistics, proving that research is working. But in general, there is a critical vulnerability. So if we rely heavily on evidence that are digital, the value of this evidence only is true if we can really prove that none of these evidences were tampered or altered. So this is the critical point. So if a researcher stands with his research several artifacts, he must be sure that the artifacts are truly not tampered, they are legitimate. So in the initiative to provide solutions to this issue, to the issue of reproducibility, the scientific community has delivered a series of initiatives or frameworks in order to help the whole community to organize information and organizing process in order to elevate the reproducibility rate. So it's important to state that there is principles like FAIR, PRISMA, and ARRIVE that are recommendations, guidelines, or protocols that they have the objective to help scientists to organize information and to provide solid proof of their work. And also the open science movement, it's very important for this too. So the open science movement states that we need to provide science that is accessible, transparent, and reproducible. So the community is working to provide some support of evidence and robustness for science. And then to put that in place, there are today several repositories like Dryad, OSF, Zenodo, Figshare, that are repositories for artifacts. So they are very important today, and they are backed by institutions like the NSH, for instance. So they can provide a repository, a safe repository for data, for scientific data. So they usually provide support for the life cycle of our research, the preservation and archiving, and also some kind of auditability and sharing. But mostly they lack features of integrity verification and provenance, and don't provide also an audit trail to check the records. And the main goal is on sharing and not verification. So when we analyze the centralized aspect of these repositories, all of them are centralized. There is a interest point here that decentralization promotes standardization. That's important for the interoperability and for the growth of the community. But at the same time, these centralized repositories, they present a single point of control. So all researchers are very dependent on the governance of that repository. If there is a change in policy or if there is a technical failure, this single point of control can impair the access to the data. And also, decentralization can also put some layer of potential for bias, or maybe accept some kind of research and not denying access for others, or maybe a gray criteria on what kind of research can be stored there or not. So in our analysis, what we believe is that centralized repositories, they fail. This is a kind of in the line of what Tim brought on the controversy aspect of centralization, that centralization and trust, they are mutually exclusive. So here we are bringing more evidence on that. That centralization means vulnerability. So if we put all our research artifacts in a single vault, we create a single point of failure and a single point of control. There is no proofs, so the systems can track what has changed in the files that are stored. They just provide logs, not proofs. So there is no audit trail for this information. And this undermines the promise, since we cannot authenticate data, and that authentication is not independently, the trust collapses. So we don't have trust on a system that is very centralized. And then if we need to eliminate trust, we must eliminate decentralized bottleneck. So centralization is important, but it compromises a lot of trust. So in our research, we are proposing this research question that's related to the proposition of a decentralized architecture based on a blockchain and distributed file system that could verify the integrity and auditable provenance of research artifacts. And our objective here is also compare that with the current institutional repositories like Zenodo, Drive, and OSF, to check if our proposition of verifiable integrity and auditable provenance is true. And for that, we rely on several foundational pillars that I will briefly describe here, but they are very important. So the first is the research artifacts. So we'll deal with storing the assets, the digital evidence, and use a decentralized ledger, a blockchain, for that purpose. So this will use the main features of the blockchain, where transactions are logged permanently and immutable and are signed cryptographically. And for the data itself, we rely on a distributed file system called IPFS that will hold all the content. So this is a peer-to-peer network that will storage all the files and metadata related to the assets. And also provide auditable provenance, a chain of custody. So the system can automatically verify all the tracking information of a file, like ownership and historical modifications of a research asset through the entire life cycle. And also verify the authenticity So since we rely on a system based on blockchain, the proof of authenticity, it's also already built in the system. And this will prove that a data was altered or not. So this is very important for our proposition. What we also add on this solution, it's a context layer based on metadata. So all the information that is stored is based on metadata, not only for the files, the assets, but also for the projects. We rely on content identifiers that are automatically generated from IPFS. So these are digital fingerprint of any file that is stored. And also we structure the information on ontologies. So this is the main block of the semantic web, and we'll use here to provide a semantic layer that is standardized and will allow interoperability with other systems. So this is how the information is stored and organized. So these concepts integrated, they built a platform that we call DOSP. So this platform is a decentralized platform that will store all the research outputs like datasets, codes, publications, and allows an independent peer-to cryptography, allows a peer to cryptographically verify information. In our proposition here is that we'll solve the problem of reproducibility, since we are not relying in a centralized environment anymore. And it works as in an integrated architecture. So we use a Hyperledger Aurora blockchain and IPFS network to provide services for immutable records and also for content storage. The main point of innovation that we bring to our solution here is that we integrate semantic models like W3C, Provo, and MADMPs that are machine actionable data management plans. So we are bringing standards for storing research information, and that will allow us not to only to store this information, but also to integrate with other platforms if needed. And we also deliver a capacity of providing services for principal investigators, data stewards, contributors, and reviewers. And each of these roles have different permissions on the system, meaning that, for instance, the principal investigator is the owner of the project and the data sets, and he can point other contributors or data stewards to join the project with different access rights. Here I will just do a brief presentation of the architecture of the solution that we have today. So between the researcher and the blockchain and the IPFS network relies a platform where we have a web interface that the users will operate, and also a full set of APIs that will provide the functionalities needed for making transactions on the network, or sending files or data sets or any kind of artifacts to the IPFS network. So for this, we rely on the API set, and also on an Aurora client, that's the native client for the blockchain, and another client for the IPFS network. So we tried as much here to work with standard architecture. So for instance, APIs are documented in the Open API standard. And mostly the solution is using standard protocols and Rust as the main language for for the code. Here I present just an overview of the metadata. Metadata is a very important piece of information of our solution. So here we can present that IPFS will hold all the information regarding the metadata of files and of the research project also. And the network, the blockchain network, will only store the content identifiers, the hash of this content. So we believe that the blockchain is not suitable for storing heavy loads of information. So we try as much as possible to just store the information that's needed for the authenticity and provenance. So for instance, we have stored here the profile of a user, the profile and metadata of a project, the semantic of the metadata, and also the information of the files, the content identifiers of the files. So we have the separation of ducts here. Heavy loads go on the IPFS, and light loads, or the information for authenticity, is stored on the blockchain. So we call this a dual ledger approach for the system. Here I bring a brief description of a use case of a user, for instance, that is working on a project that's related to the DNA sequence. So on our platform, we can provide services for the user. So our user, like the principal investigator, set up a project, and this information is uploaded to both the IPFS and the blockchain. After that, in step 2, files related to DNA sequence, for instance, are uploaded to the platform and stored on IPFS with references stored on the blockchain. All the information on step 3 is related to the metadata and the checksum of the metadata. So this is very important to make sure that if the metadata or the files of the project are in any moment changed, there will be a registration of this information on the blockchain. Then after that, we can build a knowledge graph just to organize semantically the information. And then in step 5, if needed, the system can provide a complete trail of the files and the project, and point if there is any kind of change or malicious tempered on the files. So this is a simple use case in 5 steps of what we provide already in the platform. Okay, so just to present all the project, we started this project in my master's in 2024, and then the phase 1 of the project, we had some basic services on the view 1 release of the Iroha blockchain with a Python SDK presenting Jupyter Notebooks interface and smart contracts integration. For the phase 2 that we are working now at this moment, we have a total refactor of the platform and put some very important enhancements, such as upgrading the blockchain for V2, replacing Python for Rust, and relying on APIs or in the standard of Open API. Bringing also integration with standards for data project management, like DMP, adding the whole cryptographic proofing and role-based access control. So each user has its own proper rights in the platform. So what we aim for the phase 3 is to create a version like 2.5 of the platform where we keep the core services and add trust chain for the authentication and authorization of the users as the proof of identity of the users, and hopefully also the private key for signing transactions. File exchange for exchange of private artifacts that should be exchanged between two parts safely. And important that we can provide also a client application that will mainly support all the operations on the platform, but also include the trust chain interface and the fair exchange also. And put this platform on a production grade system so we can prepare that for production. And phase 4, our main objective is to go live on a real scenario using setting a cluster for INCT, that's our institute in Brazil for research, and perform benchmarks and obtain a real world validation. So there is a lot of work from now on, but we are very confident that we can achieve that. And for final, I'd like to bring some conclusions that our objective here is to shift the open science from a passive repository to an active cryptographically secure engineering framework. So we bring all the features of the decentralized technologies and along with data standards to provide a platform that is capable of enforcing data integrity and verifiable lineage and provenance. So for this, we use a hybrid model on Iroha as the blockchain and IPFS as the storage. Our proposition also includes provenance for all the steps of the user operation on the project level and also on the artifact levels, well aligned with standards that we believe that's very important for interoperability. And the objective is to create a true infrastructure for reproducibility. Also adding the self-sovereign identity and algorithmic fair exchange as future modules. So with that, I conclude my presentation and open for Q&A.
Okay. Thank you very much, Eduardo, for your presentation. So, questions? Any question? So, Tim, as you can see, we've become part of this national program, the ENCT, the National Institute. I think it's for Science and Technology. That's the name. Professor Chago is the local coordinator here. And ENCT, well, we aim to apply or to use this possibility as a possible application of Eduardo's platform. So our intention is to make available this DOSP platform that Eduardo is developing to the NCT. And what is missing right now, I would say that we have a first version of this authentication system that Eduardo has developed and included in DOSP. And now we are changing, and our intention is to replace it by Trust Chain, and possibly to, of course, for Eduardo to get to know Trust Chain, and maybe to have another use case that we can apply Trust Chain while we study it and get more knowledge about this technology. So yeah, so the trust chain is also in our roadmap in Eduardo's research too. Okay, Tim, go ahead.
Yeah, thanks. I mean, this is great. This is really interesting. I think it's another nice use case because presumably the idea is that the scientist essentially or the group of scientists that have actually generated the artifacts, they're the proper authority to attest to the veracity of the data and the quality of the data that they've produced, and they're going to be affiliated to some organization. They're going to have they're going to have sort of credentials in some sense, and so it's a natural. I think it's natural to sort of say, look, this, if you want to verify that artifact, you want to say, right, who produced it, and I guess when was it produced, and what's their institutional affiliation, and what's the right way to see that? Well, those signatures should kind of cascade down in exactly that, in that hierarchy. So I think whenever we have this credentials, we call them sort of data credentials, essentially is the way that it's referred to in trust chain already, for data provenance. And it is necessarily a hierarchical thing. Some people see that as a big tension between like the idea of decentralization, and yet you've still got this hierarchy of attestation and of sort of issuance of the credentials. But I don't really see that it's a big tension. I think you have these natural hierarchies, but you want to trust the producers of the data of in this case, or the issuers of the credentials in general. But that's that doesn't mean that the whole system has to be centralized. I think it makes sense for it to be more kind of organic and bottom up, and then you can start on a small scale, but then you can increase the size of that network as more and more scientists hopefully participate. So I think it's a very natural use case. I did have one question about what you mentioned, the kind of the features of the blockchain, the Hyperledger Iroha. I'm not familiar really, so I wonder if you could say something about I'd be interested if I'm verifying, or if I want to kind of I want to judge this artifact. I don't know, at what point is the blockchain sort of doing some heavy lifting, or what actual what do the features of that blockchain sort of add to that?
Okay, so the main part here is that we have a separation of duties. So we have the research artifacts are truly storage on the IPFS side. Okay, so for each file or storage there, we got the content identifier, the CID, and this content identifier is registered on the ledger on the Iroha blockchain. So we have this as the main point for verification. So if we have the CID in both sides equal, we can validate that the file is original, that was not tampered. That's the main concept of the whole architecture. So we are relying on this for verification, and also we track the activity of the changes on the blockchain to provide the provenance. So if this file was stored like 100 days ago, we have all the information, so we can backtrack and search for the modification in the blocks, see where that CID is stored and what happened from them or today.
Okay, that makes sense. That's interesting, because one of the things that we kind of wrestled with a bit is the idea that if sometimes these data artifacts are going to be really large, and so you generate a hash for the original data, but is it one hash for the entire data set, or how and then if there's then some processing of that data and it produces another large data set, is it possible to kind of in some sense capture the difference, the delta between the original and instead of having to sort of hash everything as a completely unique thing. So I don't know if I don't know if there's a lot of work on that. I think there's some commercial work, but I don't know maybe if it has features that enable you to sort of track provenance sort of incrementally. That might be interesting.
Yeah, that's a very interesting idea. For this moment, the implementation consider regenerating a new hash for each storage, and so that's a kind of heavy. But this idea of just getting the diff could be a very interesting approach. Thank you.
Okay, thank you very much. Carlos? Carlos, go ahead.
Yeah, sorry, Eduardo. I think I'm walking backwards with a general question. So I think I missed some of the first slides. I think I was distracted. Sorry if you need to repeat that. So your claim is that some experiments, Chagos experiments, cannot be reproducible. Yeah, they cannot be repeated to be double checked. Yeah, that's the claim, and there are several factors, several hurdles that have to be avoided to repeat experiments. And you're addressing one or some of the technical problems there that prevent repetition of experiments. I miss it. So what is the main technical problem you are trying to solve with a platform? I think you have said that before, but I just wanted, I want you to refresh my mind. So what is the main problem again?
Okay, Professor Carlos. The main problem we are trying to address here is the artifact handling. So we believe that when artifacts are handling the traditional way in a centralized system, you cannot easily prove that the artifact is legitimate, that was not changed in any fashion. So our main issue that we are seeking here to solve is that we can, if we bring this artifact and store it on a decentralized platform, we can improve the proof that file it's not altered and it's not tempered.
So it's about trusting the
Yeah.
provenance data. It's trusting what the provenance and the quality, or no, it's a way of verifying, a way of having a mechanism for the researcher, about having a mechanism that helps her or him to verify cryptographically and systematically provenance, who produced the data,
Yeah.
and also the quality of the data. Is that correct? This is the impression I get.
The idea is more related to the first part of your comment. Is more related to the trust. So we can make sure that when the file is stored on a decentralized network, as we propose, this file will be set to be analyzed. The file will be analyzed to be or with full integrity or not. We don't go to the quality side of that information. We just go to and focus on the integrity of the information. And for that, what's important, that our proposition relies on the properties of the blockchain itself, the cryptographic properties of the blockchain. We are not trying to reinvent the wheel here. We are just using the cryptographic properties of the blockchain. Meaning, whenever a transaction is performed on the blockchain, you have a hash, and that hash means a file that was stored on the IPFS. So we can prove that if the file exists on the IPFS network and its hash has its encounter, its storage on the blockchain, and both coincide, both are the same, we can say the file has full integrity.
Right. So using the blockchain, going back to Tim's question, to provide evidence that the file that I am using, I am the researcher, has not been fiddled with, so that the integrity of the file. So the blockchain is providing me a mechanism to verify the integrity of the file, so that I can trust the data in the file and I can use it safely, because I know that it's genuine. Nobody has fiddled with that data. Yeah. So that okay. And also, the blockchain, going back to the ideas now, is going to provide me evidence that the file A that I'm using for this experiment E, has been produced by Unijuit or by some researcher, Fabricia, from University of Ijuit. So you're using the blockchain for that. This is what I can understand. So that the platform that you are building is going to have mechanisms to access the blockchain, to be able to verify those two requirements to trust the data that I'm using in my experiment. I'm guessing. Tell me if I.
You got that. That's the proposition. So that's very important for us, that we also can identify the user. So that's we are approaching using trust chain for instance for that, because once you have an identity for the user, we provide evidence of the file, and also an evidence who is the owner of that information, of that file, or who can use that, because we know who is the user. We can prove who is the user. We have a clear identity of him or her.
Okay, so thank you, Carlos. I'm sorry, the discussion is very interesting and good, but we are quite behind our schedule here. So we need to move forward. We have one more presentation by Carla. So thank you very much, Eduardo, for your presentation.
Thank you all. Thanks.